All right, so let's take a look at this worst case scenario and at least take together the opportunity to set up the process of subtracting 3 over 2x squared minus 5x minus 7 minus 1 over 2x squared minus 11x plus 14. What's our first objective in this problem? If I'm meant to subtract these two fractions, what do I need? I need a common denominator, just like before, right? Unless the denominators that we start out with are already identical, it's up to us to go through the process of determining a common footing on which to put them so that they can be subtracted. All right, well, here's the thing about rational expressions. It's going to be probably easier for us to work with these two denominators and to work with the rational expressions in which they appear if we have a different understanding of how these polynomials are put together. Certainly one way of finding a common denominator would have been just to multiply these two denominators across, the way that we did before. That will work just fine. The problem is that at some point, when it comes time to simplify our answer, we're going to need to know not just how these polynomials are put together with respect to addition and subtraction, but also instead with respect to multiplication and division. If we find that out up front, we might be able to save ourselves a little bit of work along the way. See, the thing about adding fractions or adding rational expressions is that sooner or later, you have to reduce something into its lowest terms. And so it's better to understand what those factors are that go into those lowest terms, maybe sooner rather than later in the process. All of which is to say the following. Why don't we try to understand each of these denominators in terms of the factors that comprise it rather than the terms? By that which is multiplied or divided to make these expressions rather than that which is added or subtracted. This is my sneaky way of getting us to think about Module 8 factoring techniques again. Let's try and factor each of these expressions first. Because if they share a factor in common, we may be able to get away with doing a little bit less work in finding a common denominator for these two fractions. So, somebody remind me how I could go about factoring 2x squared minus 5x minus 7. What's our technique? What am I looking for? All right, so I need a pair of numbers which, when I add them together, gives me negative 5. That negative 5 coming from the middle term, a coefficient of the x to the first power here, often called b. And when I multiply them together, what am I supposed to get? So negative 7 is our c coefficient, but the thing is, we also have a coefficient in front of the x squared, which is going to mess around with us if we just consider the minus 7 by itself. So what do I want the product to be, in fact? Not just negative 7, but 14. Negative 14. Because that's what we get when we multiply a times c. So this is the AC method for factoring a quadratic trinomial whose leading coefficient is not equal to 1. So, what is my pair of numbers whose product is negative 14 and whose sum is negative 5? How about negative 7 and positive 2? So there is the winner of our AC factorization game in this example, which allows me to split the middle term into negative 7x plus 2x. And then from there, my favorite way of proceeding is just to put our little factorization grid together and put it together in a way that gives me 2x squared in the upper left-hand box. That gives me negative 7x in the next box, and then 2x minus 7. So our four terms that we're trying to factor go into our grid. And then we pick on the first row and say, what's the greatest common factor between 2x squared and negative 7x? Well, What is the greatest common factor there? Yeah, so the only power of x that we can end up with is x to the first power, and 2 and 7 share nothing in common. So the greatest common factor of that pair of terms is just x. And then what do I multiply x by in order to get 2x squared? What goes here? What belongs in that? So I need an x to make the x squared, but I also need a 2 to account for the 2 coefficient. How about right there? What do I multiply x by in order to get negative 7x? Negative 7. And finally, what do I have to multiply both of those things by in order to get 2x and negative 7 respectively in the last row? Two x times what gives me 2x? 1. And sure enough, negative 7 times 1 also gives me negative 7. All of which is to say, how does this denominator factor? What are the two binomial factors that we get? They come from that first row and that first column. X plus 1 times 2x minus 7. So there is an AC method factorization for the denominator of our first fraction. So I'm just going to take the liberty of going up to our first fraction and replacing its denominator with x plus 1 times 2x minus 7. The same process applied to our second trinomial. Just to repeat this process, here the middle term is negative 11, and a times c is going to be positive 28. And so instead of negative 7 and 2 winning this game, this time we have negative 7 and negative 4. Double check that one on your own. They multiply together to give us positive 28, and they add together to give us negative 11. So that my middle term splits into minus 7x minus 4x. And then my constant here at the end is 14. If I look for the greatest common factor in the first row, it is yet again equal to x. And the cofactor that I get is again 2x minus 7 on the outside. So looking at the first row now works. And it's when we move to the second row that we get something different. You can check that what we get is negative minus 2, because 2x times negative 2 gives me negative 4x. Negative 7 times negative 2 gives me positive 14. So our second denominator factors as x minus 2 times 2x minus 7. X minus 2 times 2x minus 7. So I think that was probably the hard step, is getting these two expressions factored. And now here's the payoff, and this is what I want to close with. Rather than finishing out this entire example, I just want to kind of take a look at what would happen next. And hopefully convince you that this process of factoring that we just hard fought for can save us a little bit of time. Based on how these factors shake out, what is a common denominator that I can use for these two fractions? What factors does it need to have, my common denominator? Okay.
X plus 1, 2.
Yeah. So I've got to have an x plus 1 because I need this denominator to be a multiple of the denominator of the first fraction. Likewise, I need to have a 2x minus 7 so that my first denominator can go evenly into my new denominator. I also need an x minus 2 so that my second denominator can go evenly into my common denominator. Why don't I need another 2x minus 7? Because that's what we would get if we just multiplied straight across. I have it in common, exactly. I don't need it in there twice because it appears common to both of our original denominators. That makes this quantity that we just wrote down the least common multiple of these two denominators, or in short, the least common denominator for these two fractions. So that's the sense in which we get to economize just a little bit at this stage. We don't have to multiply the 2x minus 7 factor in there twice because it's common to both of our original denominators. 2x minus 7, x minus 2. And because we put in that effort up front, this next step should be a little bit more straightforward for us. Because what do I have to multiply the first fraction by in order to turn its denominator into the common denominator? What's the missing factor? X minus 2. That's all that we've multiplied by downstairs in the first fraction. So what should I do upstairs? I got to multiply by x minus 2. So my first fraction is going to have its new numerator be 3 times x minus 2. Ditto for the second fraction. What have we multiplied the second denominator by in order to turn it into the common denominator? What's the missing factor? X plus 1. And at no point have we had to multiply by the 2x minus 7. That's the advantage of this process, is that that factor which was common to the first and second fractions denominators does not have to be then repeated when we go to rebalance these two fractions. And so now our two fractions are on a common footing, which means that in order to subtract them, we just have to subtract their numerators. X plus 1, 2x minus 7. The denominator remains the same as usual. And upstairs in the numerators, we just end up with 3 times the quantity x plus 2, minus 1 times the quantity x minus 1, and I've got a sign error here. Where's my sign error? It's in this first thing, x minus 2. There we go, and I think it's x plus 1 that I wanted here in the second fraction. Sorry, I've got some signs out of place. And it's okay to have signs out of place as long as you catch them before you go any further. So there we go. And then to finish, all I would do is I would try to simplify the numerator to the extent that it's possible by distributing the multiplication across the addition and subtraction and combining like terms. And I'm going to do that step maybe more quickly than we are all comfortable with, just in the interest of time. 3x minus 6 minus x minus 1 is going to give me 2x minus 7. Uh-oh. Uh-oh. Huh, I thought we were in the clear. But in fact, this may not be completely simplified. What's my last step? Cancel. What can I cancel? 2x minus 7. That factor is common to the numerator and the denominator. So we can get rid of it. We can divide by it, which in the denominator is going to leave me with nothing but x plus 1 times x minus 2. What does it leave me with upstairs? If we cancel everything, every factor, what's left behind? 1, yeah. Sometimes I'll see people write 0 or just leave it blank up there. No, we leave a 1 behind because when you cancel, what you're really doing is you're really dividing by that factor. Dividing by 2x minus 7, upstairs and downstairs. And when I divide 2x minus 7 by itself, what happens is what happens when we divide any quantity, non-zero quantity, by itself. It leaves the number 1 behind. And then we're done. So that is a worst-case scenario. We had these two quadratic denominators, which had leading coefficients that were not 1, and so that already set a higher bar for their factorization than otherwise we might have. So we employed an AC factoring method technique to break them apart. And then we discovered that when we did that, they actually shared a factor in common. And we leveraged that fact here. because it allowed us to choose a least common denominator that didn't include all the factors of the first and second repeated as many times as possible, but included them as a minimum number of times possible. So the 2x minus 7 only appeared once in those denominators, which made our process of rebalancing the numerators a little bit cleaner. And it also made it easier for us at the end to spot that our numerator, 2x minus 7, had a factor of 2x minus 7 that we can cancel to get our completely simplified final answer.